September 16, 1943. Bougainville, Solomon Islands. First Lieutenant Kenneth Walsh studied his hand as he recorded observations in his personal log, documenting what would become a pivotal moment in Pacific air warfare. The new aircraft changes everything. Speed and firepower give us advantages the Zero cannot match. What we need now is better accuracy in deflection shooting. Through the scratched plexiglass of his F4U Corsair's canopy, Walsh had just returned from escorting Navy bombers, witnessing the challenges that plagued even experienced pilots. Hitting a maneuvering target while both aircraft executed violent turns required mathematical calculations that human minds struggled to perform in fractions of a second. What Walsh and thousands of other Marine and Navy pilots could not yet know was that British engineers had already solved this problem. A device incorporating spinning gyroscopes and precision mirrors would soon transform aerial gunnery from an art requiring years of experience into a science that could be mastered in weeks. The Mark 118 gyroscopic gun sight would arrive in the Pacific theater within 12 months, fundamentally altering the mathematics of air combat. The VA F4U Corsair had entered combat in February 1943, bringing unprecedented speed and firepower to marine aviation. Powered by the Pratt & Whitney R28,000 double wasp engine producing over 2,000 horsepower, the Corsair could exceed 400 miles per hour, making it the first American single-engine fighter to break that threshold. Its 6 Browning M2 machine guns, each firing 50 caliber ammunition at nearly 800 rounds per minute, delivered devastating firepower when bullets found their target. The challenge was making those bullets connect. Deflection shooting, the art of hitting a moving target from a moving platform, represented the single most difficult aspect of aerial combat. When a Corsair traveling at 400 miles per hour attempted to shoot a Zero, executing evasive maneuvers at 300 miles per hour, the pilot had to aim not at where the enemy was but where he would be when the bullets arrived. Those bullets, leaving the guns at approximately 2,700 foot-pulse, still required time to reach their target. At 500 yards, that time approached half a second. In that interval, a Zero in a standard rate turn would move nearly 200 foot. The pilot had to lead the target by that exact amount, adjusting continuously as ranges and angles changed, all while pulling forces that narrowed vision and made complex mathematics impossible. The Mark 8 reflector sight, standard equipment on Corsairs through 1943 and early 1944, offered no assistance with this fundamental problem. It projected a simple illuminated reticle onto a glass plate, nothing more than a fixed reference point showing where the guns were aimed. The pilot had to estimate lead angle entirely through experience and intuition. Talented pilots developed a feel for deflection shooting after months of practice. Many pilots never developed that feel at all, consistently firing behind fleeing targets and wasting ammunition that had traveled 6,000 m across the Pacific. Lieutenant Kenneth Walsh, flying with VMF 124, had mastered deflection shooting through sheer repetition and natural ability. On May 13, 1943, he became the first Corsair ace by shooting down 3 Japanese fighters, bringing his total to 6 confirmed victories. Walsh had learned to anticipate target movement, to sense the proper lead angle, to fire at the precise moment when geometry and instinct aligned. His success came from hundreds of hours of practice and an innate understanding of three-dimensional motion. Most pilots lacked Walsh's gifts. The average Marine pilot arrived in the combat zone with perhaps 200 hours of total flight time. Maybe 20 hours of gunnery practice against towed targets that flew straight and level against maneuvering Zeros flown by experienced Japanese pilots. These average pilots struggled to achieve hits. Combat reports from 1943 show that many pilots expended all their ammunition without scoring a single victory, their bullets passing harmlessly behind targets because mental calculations were fractions of a second too slow. The British had recognized this problem early in the war. In 1941, Fanti began producing the 2 Malawian Kwacha's Gyro sight, a revolutionary device that used spinning gyroscopes to automatically calculate deflection angles. The principle was elegantly simple. Gyroscopes resist changes in orientation. When an aircraft turns, the gyroscopes inside the sight remain pointed in their original direction while the aircraft rotates around them. By measuring this resistance through precision gears and mirrors, the sight calculates the aircraft's rate of turn. That rate of turn directly corresponds to the lead angle required to hit a target. The sight automatically adjusts the aiming reticle to compensate, moving it ahead of the target by precisely the correct amount. Royal Air Force pilots using the 2 Malawian Quachas GRO sight reported dramatic improvements in accuracy. Spitfire pilots who had struggled with deflection shooting suddenly found themselves hitting targets on their first burst. The sight eliminated the need for complex mental calculations, allowing pilots to focus on tactics and positioning rather than geometry. The United States recognized the technology's potential immediately and contracted Sperry Gyroscope Company to produce American versions. The U.S. Army Air Force designated their version the K-14, while the Navy and Marine Corps called theirs the Mark 18. Both were essentially identical to the British M2 with minor modifications for American manufacturing techniques and cockpit integration. Sperry's facility in Lake Success, New York employed over 20,000 workers at peak production, turning out gyroscopic gun sights alongside bomb sights, fire control systems, and navigational equipment. The Mark 18 was substantially larger than the simple reflector sight it replaced. Where the Mark 8 was a compact unit weighing perhaps 5 pounds, the gyroscopic sight system weighed 12 pounds and required significant cockpit modifications. Sperry engineers explained that the bulk was necessary. Inside the housing were 2 independent gyroscopes measuring pitch and yaw, spinning continuously once powered. These gyroscopes contained the secret to solving deflection shooting, the single most difficult aspect of aerial gunnery that had challenged fighter pilots since the First World War. The Mark 18's design incorporated lessons learned from British combat experience. The sight featured 2 independent reticles visible to the pilot. On the left side, a fixed cross indicated where the guns were actually pointed, providing a reference for the aircraft's bore axis. On the right side, a gyro-stabilized reticle consisting of a center circle surrounded by 6 diamond-shaped pips showed the computed aiming point. As the pilot maneuvered to track a target, the gyroscopic reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle. The pilot's procedure simplified dramatically compared to reflector sight operation. First, he set the target's wingspan using a control on the sight itself, selecting from known values for Japanese aircraft types. The A6M0, most common opponent in the Pacific, had a wingspan of 36 feet for standard variants. With wingspan selected, the pilot adjusted a twist grip integrated into the throttle lever to expand or contract the diamond-shaped ranging reticle until it matched the apparent wingspan of the target as seen through the sight. This action mechanically set the range, informing the sight's ballistic computer how far away the target was and therefore how much bullet drop to compensate for. With range and wingspan set, the gyroscopes took over. As the pilot maneuvered to track the target, the moving reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle for the current rate of turn. The pilot simply had to place that computed reticle on the target and press the trigger. The bullets would arrive precisely where the sight predicted, regardless of the complexity of the maneuvering. Production of the K-14 and Mark 18 began in earnest during spring 1944. The U.S. Army Air Force received priority for European theater operations with P-51 Mustangs and P-47 Thunderbolts receiving K-14 installations beginning in August 1944. The Navy and Marine Corps followed closely with F4U Corsair and F-6F Hellcat scheduled for Mark 18 retrofits through fall and winter 1944. The first Corsair squadrons to receive the Mark 118 were those preparing for carrier operations. VMF 124 and VMF 213. The first Marine fighter squadrons assigned to fleet carriers received their gyroscopic sights during training at Naval Air Station Santa Barbara in late 1944. The squadrons would join USS Essex in December, bringing the Corsair into carrier-based combat for the first time. Lieutenant Robert McClure, flying with the reformed VMF 214, received his Mark 18 equipped Corsair in early 1945. McClure had scored several victories during 1944 using the standard reflector sight, but he immediately recognized the gyroscopic sight's revolutionary potential. In a letter to his family, later preserved in Marine Corps archives, McClure wrote that the Mark 18 represented the difference between skilled guesswork and mechanical certainty. The device compressed years of experience into a few hours of training. Japanese Naval Aviation Intelligence first became aware of American gyroscopic gunsight technology in late 1944 through analysis of recovered Corsair wreckage and interrogation of captured documents. What they discovered alarmed them profoundly. Technical specifications confirmed that Americans had developed a fire control system that largely eliminated human error in deflection shooting. Japanese tacticians understood immediately that this technological advantage could not be countered through improved training or modified tactics. The mathematical precision of gyroscopes spinning thousands of times per minute could not be matched by human reflexes, no matter how experienced the pilot. Japanese fighters had survived thus far by exploiting their superior maneuverability to force American pilots into difficult deflection shots where human calculation errors provided some margin of safety. Against Mark 18 equipped Corsairs, that margin vanished. Any American pilot who could track a Japanese fighter long enough to set range would score a hit regardless of the complexity of the maneuvering involved. Tactical modifications were ordered across all Japanese naval aviation units. Japanese fighters were instructed to avoid prolonged turning engagements with Corsairs at all costs. The new doctrine emphasized hit and run attacks, diving from altitude to make a single pass before extending away at maximum speed. This tactical shift acknowledged an uncomfortable reality that Japanese pilots could no longer rely on maneuverability alone to survive against technologically superior gun sights. December 1944 brought a significant milestone in Corsair operations. VMF 124, commanded by Major William Gizer, became the first Marine fighter squadron to operate from a fleet carrier when they joined USS Essex at Uli. VMF 213 joined simultaneously, bringing 48 F4U Corsair to carrier operations. Both squadrons were equipped with Mark 18 gyroscopic gun sights, representing the cutting edge of American aviation technology. The Essex Air Group sorted in January 1945 for strikes against Formosa and the Philippines. Marine Corps air pilots flew combat air patrol, bomber escort, and strike missions, finally bringing the F4U into the carrier-based role for which it had originally been designed. The Mark 18 proved invaluable during these operations. Pilots engaging Japanese interceptors reported significantly improved hit rates compared to their previous experiences with reflector sights. Combat action reports from January and February 1945 document numerous instances where pilots achieved kills with their initial burst, a level of first-pass success that had been uncommon with earlier sighting systems. The difference was most apparent during bomber escort missions where Corsairs maintained formation positions that often prevented ideal attack geometries. The Mark 18's ability to calculate accurate deflection from any angle transformed these constrained engagements into opportunities rather than disadvantages. Pilots no longer needed to maneuver into perfect 6 o'clock positions. They could engage from deflection angles that would have been impractical with reflector sights. February 1945 brought the invasion of Uema, where Marine Corsair provided continuous air cover for the assault force. Multiple Marine squadrons flew from escort carriers, maintaining combat air patrols over the invasion fleet and supporting ground operations. The Mark 18 equipped aircraft demonstrated their effectiveness during defensive missions against Japanese air attacks. Pilots intercepting incoming raids consistently achieved kills at ranges and angles that would have been difficult with older sighting systems. The gyroscopic sight's automatic deflection calculation allowed pilots to engage multiple targets in rapid succession, where a pilot with a reflector sight might have expended all ammunition on a single difficult target. Mark 18 equipped pilots could achieve hits on 2 or 3 targets during the same engagement, conserving ammunition and multiplying their effective combat power. Squadron commanders noted in operational reports that less experienced pilots were achieving combat effectiveness comparable to veterans, primarily due to the improved fire control provided by the gyroscopic sight. March 1945 saw the continuation of carrier operations against the Japanese home islands. VMF 214 aboard USS Franklin participated in strikes against Japanese airfields and installations. On March 19, 1945, Franklin was hit by a Japanese bomber while operating off Kyushu. The resulting explosions and fires killed over 700 men aboard the carrier, including 32 members of VMF 214. The squadron suffered devastating casualties, but the survivors continued operations after the Franklin limped to safety. The disaster highlighted both the dangers of carrier aviation and the courage of the pilots who flew these missions. Despite the losses, Marine Corsair squadrons continued their mission, providing air cover and strike capability for the fleet. April 1945 brought Operation Iceberg, the invasion of Okinawa. This campaign would witness the most intensive kamikaze attacks of the war, with Japanese forces throwing thousands of aircraft against the American fleet. In desperate attempts to halt the invasion, Marine Corsairs equipped with Mark 18 sights played a crucial role in defending against these attacks. The gyroscopic sight proved particularly effective against kamikaze aircraft, which flew predictable attack profiles that made range estimation and deflection calculation straightforward. Pilots could acquire incoming kamikazes, set range using the sight's ranging reticle, and achieve first burst hits with regularity that would have been impossible with reflector sights. Combat air patrol missions during April through June 1945 resulted in hundreds of Japanese aircraft destroyed. While precise statistics specifically attributing kills to Mark 18 equipped aircraft versus those with reflector sights are not available in declassified records, operational reports consistently noted improved combat effectiveness among squadrons that had received the gyroscopic sights. The psychological impact on Japanese pilots who survived encounters with Mark 18 equipped Corsairs extended beyond simple tactical disadvantage. The experience of being hit, regardless of evasive maneuvering, of watching tracers curve through the air with unnatural accuracy, created a sense of technological helplessness that traditional training had not prepared them for. Post-war interviews with Japanese aviators revealed that many identified advanced American fire control systems as among the most demoralizing technologies they faced. The certainty of being hit once an American pilot achieved a tracking solution eliminated the hope that had sustained Japanese fighter pilots through increasingly desperate circumstances. Maneuverability could no longer save them. Experience provided no advantage. And the only escape was to avoid engagement entirely, a tactical impossibility when defending against attacking bombers or protecting their own surface forces. The Mark 18's technical operation represented a remarkable achievement in mechanical computing. The system operated without electronics, using purely mechanical linkages, gears, and mirrors to perform calculations that would challenge a trained mathematician. The gyroscope spun continuously once the sight was powered, maintaining their orientation in space through conservation of angular momentum. As the aircraft maneuvered, the gyroscope housings rotated relative to the stable gyroscope rotors. Precision gears measured this relative motion, translating it into mirror movements that repositioned the aiming reticle. The entire system operated with tolerances measured in thousandth of an inch. Manufactured using the most advanced machining techniques available in 1944, Sperry's production facilities represented the pinnacle of American precision manufacturing. Each Mark 18 required dozens of individual components machined to exacting specifications. The gyroscopes themselves were masterpieces of miniaturization, spinning bearings that had to operate smoothly under sustained hygiene, maneuvering without binding or failing. Quality control procedures tested each sight extensively before delivery. Test stands simulated aircraft maneuvering, verifying that the sight correctly computed deflection angles across a range of turn rates and target ranges. Sights that failed these tests were returned for adjustment or rebuilding. The manufacturing challenge was not just producing the sights, but producing them in sufficient quantities to equip thousands of aircraft across multiple theaters. Sperry ramped up production throughout 1944, training workers in the specialized skills required for precision optical and mechanical assembly. The Mark 18 benefited from American mass production techniques while maintaining the quality standards necessary for a precision instrument. Parts were designed for interchangeability, allowing sights to be assembled from components manufactured at different facilities. This modularity also simplified maintenance and repair in forward areas. If a sight failed in combat, technicians could replace individual components rather than the entire unit. Spare parts were stocked at maintenance facilities throughout the Pacific, ensuring minimal downtime for aircraft requiring sight replacement. The integration of the Mark 18 into Corsair cockpits required careful attention to ergonomics. The sight had to be positioned where the pilot could easily view it while maintaining situational awareness. The throttle-mounted range adjustment had to be accessible without requiring the pilot to remove his hand from primary flight controls. Engineers worked with experienced combat pilots to refine the installation, incorporating feedback about what worked and what created difficulties during high-stress combat maneuvering. The result was a system that pilots could operate intuitively without needing to divert attention from tactical decision-making. Training programs were developed to teach pilots how to use the Mark 118 effectively. The training emphasized understanding what the sight was showing and how to interpret its indications. Pilots learned to recognize when the sight had stabilized after violent maneuvers, when to trust the computed reticle, and how to quickly set range using the diamond-shaped ranging pattern. Ground school instruction covered the basic principles of gyroscopic deflection computation without overwhelming pilots with mathematical theory. The goal was practical proficiency rather than engineering understanding. Pilots needed to know how to operate the sight, not how to design one. Flight training included practice intercepts against target aircraft, allowing pilots to experience how the sight behaved during actual tracking situations. Instructors emphasized the importance of smooth tracking since erratic maneuvering could cause the gyroscopes to momentarily lose accuracy. The Mark 118 worked best when the pilot maintained steady pursuit, allowing the gyroscopes to measure consistent turn rates. Training also covered the sight's limitations. The gyroscopes required several seconds to stabilize after violent maneuvers. If a pilot executed a sudden reversal, the sight's reticle would lag briefly before reacquiring accurate deflection information. Experienced pilots learned to anticipate these limitations, timing their attacks to coincide with periods when the sight had achieved stable operation. Despite these minor limitations, the Mark 118 represented a quantum leap forward in fire control technology. Pilots who had struggled with deflection shooting using reflector sights found themselves achieving hits with regularity that had previously seemed impossible. The sight didn't make aerial combat easy, but it removed one of the most difficult variables from the equation. Combat remained dangerous and demanding, requiring tactical judgment, situational awareness, and skilled flying. But the actual act of shooting, the moment when trigger met target, had become more predictable, more reliable, and more lethal. The cumulative impact of the Mark 118 on Corsair operations in 1945 is difficult to quantify precisely from available records. Official statistics document that F4U Corsairs achieved an overall kill ratio of 11-to-1 during World War II with 2,140 air combat victories against 189 losses to enemy aircraft across 64,051 operational sorties. These figures represent the combined results of aircraft equipped with both reflector sights and gyroscopic sights across the entire war. Separating the specific contribution of the Mark 118 from other factors would require access to detailed combat action reports that remain classified or unavailable. What can be documented is the consistent testimony of pilots who flew with both sight types. These pilots uniformly reported that the Mark 118 made deflection shooting more reliable and less dependent on natural ability. Anecdotal evidence from squadron records, pilot memoirs, and operational summaries indicates that the gyroscopic sight provided significant practical advantages in combat. The Mark 118 program represented American technological and industrial capability at its peak. The device incorporated cutting-edge gyroscopic technology, precision optics, and mechanical computing, all packaged in a form that could withstand the brutal environment of combat aviation. It was manufactured in quantities sufficient to equip thousands of aircraft, distributed across a global supply chain, and maintained in forward areas by technicians working under primitive conditions. The program succeeded not because of any single brilliant innovation but because the entire system functioned effectively. British scientists identified the principle. American engineers adapted the design for mass production. American industry manufactured the units in volume and American logistics delivered them where they were needed. The Mark 118 exemplified the systematic approach to military technology that characterized American war production. The Japanese perspective on the Mark 118 and similar Allied fire control technologies evolved in the post-war decades as former aviators published memoirs and participated in historical analyses. The universal conclusion was that American fire control technology had rendered Japanese tactical doctrine increasingly ineffective by late 1944 and early 1945. The maneuverable fighter, piloted by well-trained aviators, could not compete against aircraft equipped with systems that calculated deflection automatically. Japanese post-war aviation development reflected these lessons learned. The Japan Self-Defense Force, established in the 1950s, emphasized advanced avionics and weapons systems over aircraft maneuverability. The pilots who had survived combat against Mark I-18 equipped Corsairs understood that future aerial warfare would be decided primarily by technology rather than individual skill alone. The Corsair itself continued in service long after World War II ended. Marine squadrons flew F4Us during the Korean War from 1950 to 1953, providing close air support for ground forces and flying interdiction missions. Many of these aircraft retained their Mark 18 gyroscopic sights throughout their operational lives. The technology that seemed revolutionary in 1944 had become standard equipment by 1950. Unremarkable and expected. This normalization of technological sophistication characterized the post-war era. Capabilities that would have been considered impossible in 1940 were routine by 1950 and obsolete by 1960. The transformation of aerial gunnery from art to science, accelerated by the Mark 18's introduction, reached its logical conclusion with guided missiles that required no pilot aiming whatsoever. Air-to-air missiles, first deployed operationally in the 1950s, eliminated even the requirement that a pilot maneuver his aircraft to point his weapons at the target. The progression from reflector sights to gyroscopic sights to radar-guided missiles occurred in less than 15 years, a pace of technological change unprecedented in military aviation history. By the time American pilots flew missions over Vietnam in the 1960s, the Mark I-18's gyroscopic principles had been incorporated into far more sophisticated fire control computers. These systems integrated radar ranging, automatic lead computation, ballistic calculation, and target identification into unified packages that bore little resemblance to the mechanical computer of 1944. Yet the fundamental principle remained identical to what the Mark I-18 had pioneered. Measure the platform's motion. Using gyroscopes, calculate the required lead angle, and present that information to the pilot in a form that made accurate shooting possible. The statistical record of World War II Corsair operations provides context for understanding the Mark 18's role in Pacific air combat. Marine and Navy Corsair squadrons flew tens of thousands of sorties against Japanese forces from 1943 through 1945. They achieved the 11-to-1 kill ratio that established the Corsair as one of the war's most successful fighters. This success resulted from multiple factors working in combination. The Corsair's speed advantage over Japanese fighters allowed pilots to control engagement geometry, choosing when to fight and when to disengage. Its rugged construction meant it could absorb battle damage that would have destroyed lighter Japanese aircraft. Its heavy armament delivered overwhelming firepower when bullets connected with targets. The Mark 18 gyroscopic sight amplified these existing advantages by making it easier to deliver the Corsair's firepower accurately. The sight didn't create the Corsair's superiority, but it enhanced what was already a formidable weapon system. Pilot quality remained crucial. The Mark I-18 helped pilots shoot accurately, but it didn't teach them tactics, situational awareness, or judgment. These skills still required experience and training. What the sight did was compress the learning curve for one specific skill, deflection shooting, that had previously required extensive practice to master. The broader historical context reveals that the Mark I-18 was one component of comprehensive American technological superiority in the Pacific War. Radar systems provided early warning and intercept control. Radio communications enabled coordinated operations. Proximity-fused anti-aircraft shells created defensive envelopes around ships. Each technology individually provided advantages. Together they created a synergistic system that Japanese forces could not match. The Mark 18 fit into this larger pattern. It wasn't a wonder weapon that single-handedly won the air war. It was a practical improvement in fire control that made already effective aircraft more effective. Its contribution was incremental rather than revolutionary. But that incremental improvement multiplied across thousands of aircraft and tens of thousands of combat engagements produced significant cumulative effects. The legacy of the Mark 18 extended beyond its direct combat application. The sight's development required unprecedented collaboration between scientists, engineers, and combat pilots. Theoretical physics. Informed gyroscope design, manufacturing engineers solved production challenges. And pilot feedback drove iterative improvements. This collaborative approach became a model for future weapons development. The procurement process also established precedents. Rather than developing entirely new technology from scratch, the United States recognized British innovation and adapted it for American production. This willingness to adopt foreign technology when it offered advantages demonstrated pragmatism that served American military aviation well. Throughout the Cold War and beyond, the manufacturing techniques developed for Mark 18 production had lasting impact beyond the specific device. Sperry's modular assembly processes where different facilities could produce interchangeable subcomponents enabled the massive production volumes that gave American forces their technological edge. Similar techniques were later applied to radar systems, aircraft engines, and eventually electronics, creating an industrial base capable of producing complex precision equipment at scales impossible for other nations to match. The pilots who flew with Mark 18 sights formed a unique generation, transitioning from instinctive gunnery to more systematic technology-assisted combat. Many continued military careers, flying jets in Korea and serving in staff positions where they shaped tactical doctrine around the capabilities that advanced fire control provided. Lieutenant Kenneth Walsh, who had become the first Corsair ace in 1943 using only a reflector sight and natural ability, ended the war with 21 confirmed victories. He received the Medal of Honor for actions on August 15, 1943 when he attacked a superior force of Japanese aircraft despite damage to his own Corsair. Walsh survived the war and remained in the Marine Corps until his retirement, eventually reaching the rank of lieutenant colonel. His career spanned the transition from instinctive aerial combat to technology-assisted engagement, from aircraft armed with machine guns to those carrying guided missiles. Walsh's experience represented the broader transformation of aerial warfare during the mid-century. Lieutenant Robert McClure, who flew with the reformed VMF 214 in 1945, survived the war with 7 confirmed victories. He remained in the Marine Corps until 1965, retiring as a colonel. In his retirement, McClure wrote about the technological transformation he had witnessed. He emphasized that while the Mark 18 made deflection shooting more reliable, it never made aerial combat safe or easy. The sight eliminated one variable in the combat equation, but countless others remained. Altitude management, energy state, situational awareness, tactical positioning. A pilot with a perfect gun sight could still be outmaneuvered, outclimbed, or simply caught unaware by an enemy he never saw coming. The technology improved effectiveness within engagements, but did not guarantee survival. The story of the Mark 18 concludes not with dramatic endings, but with gradual evolution into more sophisticated systems. As jets replaced propeller-driven fighters in the 1950s, new fire control systems replaced gyroscopic gun sights. The Mark 18 didn't suddenly fail or become worthless. It simply became outdated as faster aircraft and longer engagement ranges required more sophisticated solutions. Some Mark 18 sights remained in service aboard Corsairs flying close air support missions in Korea. Others were placed in storage or scrapped as aircraft were retired. A few were preserved in museums where they remain as tangible links to an era when mechanical computing represented cutting-edge technology. The Mark 18's legacy lives on not in physical devices which are now museum pieces, but in the principles they demonstrated and the technological lineage they initiated. Every modern fire control system, no matter how sophisticated, traces intellectual heritage back to devices like the Mark 18 that first solved fundamental problems of automated aiming. The engineers who worked on the Mark 18 contributed to knowledge that extends far beyond their specific technical achievements. They demonstrated that complex calculations could be performed mechanically with sufficient reliability for combat use. They proved that human-machine interfaces could be designed for operation under extreme stress. They showed that sophisticated technology could be manufactured at scale and maintained under field conditions. The pilots who flew with Mark 18 sights contributed their own legacy. They tested the technology under combat conditions and provided feedback that refined its design and operation. They developed tactics that exploited the sight's capabilities. Most importantly, they proved that humans could effectively partner with automated systems, neither becoming completely dependent on technology nor rejecting it as unnecessary. This balanced approach to human-machine teaming remains relevant as automation extends into more domains. The Mark 118 era offers historical examples of how such partnerships can succeed and what factors contribute to effectiveness. The Mark 118 gyroscopic gun sight deserves remembrance not because it was revolutionary or because it single-handedly changed the Pacific War. It deserves remembrance because it exemplifies the less dramatic but ultimately more important work of solving practical problems effectively. In an era that often celebrates breakthrough innovations and disruptive technologies, the Mark 118 reminds us that incremental improvements, when implemented systematically at scale, often prove more valuable than revolutionary changes that cannot be produced or deployed effectively. The device succeeded because it was practical, reliable, and adequately effective. These characteristics, while perhaps unglamorous, define technology that actually makes a difference in the real world. The Mark 118 story is ultimately a story of people solving problems. Engineers designed it. Workers built it. Logistics. Personnel delivered it. Maintainers kept it operational. Pilots used it effectively. And commanders integrated it into successful operations. Each group contributed essential elements. Without any single contribution, the program would have failed. This collaborative nature of technological success deserves emphasis. Individual genius matters, but organized effort across many individuals and organizations matters more. The Mark 118 resulted from thousands of people doing their jobs competently and conscientiously. That collective effort, more than any individual brilliance, determined the outcome. The final assessment of the Mark 18's impact must acknowledge both what can be documented and what remains uncertain. Official records confirm that the device was produced in substantial numbers, equipped numerous Corsair and Hellcat squadrons during 1944 and 1945, and received favorable evaluations from pilots who used it. Combat action. Reports indicate improved accuracy and shorter engagement times among squadrons equipped with gyroscopic sights. Pilot testimony uniformly describes the Mark 18 as a significant improvement over reflector sights for deflection. Shooting. What cannot be precisely quantified from available declassified sources is the exact statistical improvement in kill ratios specifically attributable to the sight versus other factors like pilot experience, tactical improvements, or declining Japanese opposition quality. The 11-to-1 overall Corsair kill ratio represents performance across the entire war and includes both sight types. What remains clear is that the Mark 118 represented a meaningful advance in fire control technology that provided practical advantages to the pilots who used it. It exemplified American industrial capacity, technological innovation, and systematic problem-solving. In an era where aerial combat was transitioning from individual skill to technological systems, the Mark 118 marked an important step toward the automated weapon systems that would define post-war aviation. The device succeeded because it worked reliably under combat conditions, because it could be manufactured in sufficient quantities, and because pilots could operate it effectively without extensive specialized training. These practical considerations mattered more than theoretical elegance or engineering sophistication. The Mark 18 was designed to solve a specific problem, hitting maneuvering targets during high-speed combat. It solved that problem well enough to remain in service through the Korean War, proving its value through years of operational use. For the Corsair pilots who flew with the Mark 118 in 1945, the sight was simply an effective tool that made a difficult job somewhat easier. It didn't eliminate danger or guarantee survival, but it improved their chances in combat where margins were thin and outcomes uncertain. In the broader technological history, the Mark 18 gyroscopic gun sight stands as a transitional technology. It bridged the era of instinctive aerial gunnery and the coming age of radar-guided missiles. It demonstrated that machines could perform calculations faster and more reliably than human minds, a principle that would reshape aviation and eventually extend far beyond military applications. The pilots who witnessed this transformation understood they were living through a technological revolution that would fundamentally change aerial warfare. The Mark 18 was both an ending and a beginning, the culmination of mechanical fire control and the precursor to electronic systems that would follow. Its legacy lives on in the fire control computers of modern Aircraft, sophisticated descendants of the spinning gyroscopes that first taught machines to aim. The story of Japan never expecting Gyro Gunsights to make Corsair pilot snipers is the story of technology meeting necessity, of engineering meeting combat, and of innovation meeting implementation. It is the story of how American industrial capacity and systematic problem-solving transformed aerial warfare in the Pacific, one spinning gyroscope at a time.